Hello everyone. In this second lecture we talk about more advanced topics in complex numbers. By the way, I just remembered that one other application that I forgot to mention in video of part 1 about complex numbers is in controls. When we want to analyze electric circuits, one way to analyze the electric circuits is basically when we want to, let's say that RLC circuit I mentioned in the previous example, correct? So you had this inductor, and then you had the resistor, and then you had the capacitor, and then you had this input voltage, correct? And this current is I. So one method of analysis of this electric circuit is we replace each element by an equivalent resistor, and that equivalent resistor we call it impedance. So this can be replaced by an equivalent resistor for which that resistance we call impedance, and we show it by Z is equal L times S, where this S is the S in Laplace transform. For this one it is simply R, and for this one it is going to be 1 over C times S. Then we replace this with cap I, and then this is with cap V, and then we treat the whole circuit like the bunch of resistors. Okay, so now we say this V in is equal to I times sum of these impedances, and this equation is exactly what you get if you apply Laplace transform to the ODE we derived in the previous video. If you want to know more about it, go and look at my video in the controls playlist, where I talk about modeling electric circuits, and you see more about impedance and use of complex numbers. Okay, so when we then do frequency response of the system, then we replace this S wherever you see it, we replace it with I times omega, where I is the complex I and omega is the frequency of the input. Okay, so then you can say that the impedance of the inductor is L times I omega. For R is simply R, and for this guy is 1 over C I omega. Okay, so when we apply Laplace transform and then we want to do frequency analysis on the system, frequency of the output versus input, and the output could be anything. Let's say, for example, you can take it from the two ends of this capacitor, for example, correct? When you want to analyze the frequency response of the system, then in that S of Laplace transform we replace I omega, where I is the complex I. So as I just clearly mentioned here, one of the places that this complex I is used a lot is frequency response. In frequency response of systems in classic control, we use complex numbers all the time. Okay, frequency response in there is the other one, the stability method, okay, that you can check out. So there are several, let me show you very fast here where to look for them. So this is our channel right now, and these are the playlists. And if you go down to controls, then there are 2 videos in which I talk about, or several videos actually, I talk about complex numbers, and I use complex numbers. And one of them is this Routh-Horvitz stability criterion, you might see that, but most importantly is the frequency response basics, Bode plots. Here you clearly can see lots of frequency response using complex numbers. And also, as I said, modeling electric circuits, basic modeling of electric circuits, which is here. Then you will see also impedance. Okay, so just wanted to tell you some other places where you would see complex numbers. I'm just trying to motivate you to know that complex numbers are very important for engineering. Now, not all of you might have passed or currently in the controls class, but just I'm trying to tell you in vibrations, electric circuits, controls, and so on, these complex numbers are very useful. And not only that, in the second video right now that I'm going to talk about, I'm going to show you also probably in fluid mechanics, electromagnetism, and other places, these complex numbers are very important. Okay, so there is a reason that people, mathematicians, physicians, and so on, came up with this idea of these imaginary numbers, although they don't exist, but they are very good tools for solving problems. So this video I'm about to talk about, it goes a little bit beyond the level of the previous video, and you might not need to follow it all the way to the end based on how much you need. So here I'm going to talk about functions, mappings, taking derivatives and analytic functions, and then conformal mapping, and then integral of complex functions over contours. So it can go quite a little bit beyond the level of an undergrad engineering math, but I just try to make it as short as possible and without too many proofs. So there are some functions of complex numbers that you can define, and they're all based on the definition of z being either a plus bi or r times e to the I theta, okay? And the definitions of them are rather easy. So for example, when you define the natural log of z, remember that z is r times ei theta. Okay, and you know natural log of two things multiplied is the natural log of them added together. And clearly here you will get natural log of r, natural log of an exponential. They are inverse functions, so you will get I plus theta. So that's this formula here, right? So the natural log of a complex number is natural log of its magnitude plus I times its angle. This is the real part of it, this is the imaginary part of it. So it's nothing really major, right? Or let's say if I have the exponential function e to the z, well, here I write z in terms of its real and imaginary part. So I write it as x plus I times y, and you know, if you can write it as the product of two exponentials like this, and of course e to the x stays, and then for e to the y, iy, use the Euler formula. So this is going to be cosine y plus I times sine of y. And if you multiply it, then the real portion of it is going to be e to the x cosine y, and the imaginary part of it is going to be e to the x sine of y. Okay? So when you apply, please keep that in mind, when you apply a function to a complex number, the result is again a complex number. Okay, so I'm applying a function to a complex number, and the result is again a complex number. For example, if z is x plus iy, I can call this result of fz, I can call it u plus I times v, where u and v are functions of x and y in general. So in this case, this is your u, the real part, and this is your v, the imaginary part. And as I said, this u and v in general are both functions of what? The two variables of real and imaginary part of the complex number. okay? And so you clearly can see that. That's what it is. So let me write it for you that way. Right, so you clearly see the real and imaginary part of the function f of z, or in here again you can see the real and the imaginary part. So this is the real part, this is the imaginary part. Now if you want to write it in terms of x and y, then this is going to be natural log of square root of x squared plus y squared plus I times tangent inverse of y over x. And if you want to further simplify it, you know, this is like power what? 1/2, and it can come out of the natural log. So it is going to be 1/2 natural log of x squared plus y squared plus I times tangent inverse of y over x. So again, clearly here, this is your u of x and y, the real part of the function, and this is what? V of x and y, the imaginary part of your function, okay? So this is for natural log, this is for exponential function, and so on and so forth, okay? So just trying to tell you what happens when you apply a function on a complex number. So here we got this one also covered. Then we have other functions. The two top ones are rather obvious. Cosine of z and sine of z are rather obvious. So here I'm using the definition of e to the iz, which is cosine z plus I sine z. I'm adding these two functions together, taking the average here, taking the difference divided by 2i based on the definition of e to the iz. These sines and cosines of z are clearly coming out. And let me just focus on one of them. Let's say, for example, cosine of z. So what is cosine of z? Well, based on that definition that you have over there, cosine of z is 1 over 2 exponential of iz plus exponential of negative iz. Okay, fine. Now if I replace z with x and plus iy, so this is going to be e to the I times x plus iy, and this is going to be e to the negative I times x plus iy. And if you simplify it, this is going to be ix minus y, and this is going to be negative ix plus y, correct? Because you have I squared, which is negative 1. Here you have negative I squared, which is positive 1. And if you expand it now, you know, this is exponential, correct? And so this is going to be e to the negative y times e to the ix. This is going to be e to the positive y times e to the negative ix. Right? And then for e to the ix and negative ix, you can write their definition. Correct? So this is e to the negative y times, this is cosine of x plus I times sine of x. And this is e to the positive y times cosine of negative x plus I times sine of negative x. And you know, cosine and sine of negative x are cosine of x and negative sine of x. So here, these two terms, they both share cosine. So you will get 1/2 cosine of x times e to the y plus e to the negative y, and then plus I times these both share sine of x, and it is going to be e to the negative y minus e to the positive y. Okay, so now this is this function with 1/2. This is your u of x and y, and this guy here with 1/2 is v of x and y. If you want, I can put the 1/2 behind both of them. So I make it something like this. And now you can say this is u of x and y, and this is v of x and y. Okay, and similarly, you can develop the similar thing for sine of z. Okay, so that's these definitions for cosine and sine. The hyperbolics are the same as before, except these are positive z and negative z, and there is no I, so these are very similar to how we define cosine and sine hyperbolic for real numbers. That's the exact same definition, except for real number you plug in a complex number. It is going to be very similar. And finally, we have the power function z to the c, where c can be any number. It does not need to be, in this case, any integer number. You can also write it as e to the c times natural log of z. Okay, so z to the c is equal to exponential of c times natural log of z. Why? Because the c can go inside the natural log, and this becomes e to the natural log of z to the power c. And you know e and natural log would cancel each other. So this is how you define it. And now if you use what we had for natural log of z, which was this guy here basically. So if I plug it in, it was 1/2 natural log of x squared plus y squared, and then plus I times tangent inverse of y over x. Okay, then this c will be multiplied to both, and then the exponential will be separated into a real part and imaginary part. So the real part is going to be e to the c over 2 natural log. The c over 2 can go to the power of natural log, and e and natural log would cancel out. So you will get basically x squared plus y squared to the c over 2, and times exponential of I times c tangent inverse of y over x. And clearly this thing is the magnitude to the power c, as we had earlier with any power n when n was integer. And this part is clearly going to be cosine of c tangent inverse right? And then plus a similar thing here, but with I and sine. So we just copy this, then come down here, say I times, and we click here and we paste it. But this time we are going to make this guy sine. So this is your u of x and y. This guy is your v of x and y. Okay, so in general, as I described for you here, each one of these functions will basically takes a complex number in and spit out a complex number out, where the real and imaginary part of the result are functions of the real and imaginary parts of the input in general, okay? So this is how you evaluate complex numbers. But now, as you can clearly see, what these guys are doing are a mapping. What each function is doing is a mapping. What do I mean by that? I mean, if there is a curve in the xy plane or in the imaginary plane, z, when you apply function f, then you can form a new plane formed by u and v, and in that new plane, the relation between u and v is going to be a separate relation. Now, what do I mean by that? Well, let's try to see if I can get you anything simple. Let's look at the exponential function. So I take x and y, and then u and v are e to the x cosine y, e to the x sine y, correct? So what does that mean? It means that if I go to the complex plane formed by x and y, so here your z is x plus iy. And let's say I have a like line here, like this, where here y is equal to, let's say, 2 times x, and these are two endpoints of that line. Now, if to any point on this line I apply my function f of z equal exponential of z, then I will have this new space, uv space, where this is v, this is u, and f of z is going to be written as u plus I times v. We want to know if we apply this function to each and every one of the points on this line, what is gonna be the shape of the result. And based on what we have in this slide here, this page, u is e to the x cosine y. So u is e to the x times cosine y, and v is e to the x sine y. But y and x are related by this equation. So wherever I have y, I replace it with 2x. So this is going to be e to the x cosine of 2x, and this is going to be e to the x sine 2x. Now, does that give me anything? Well, if I square u and v and add them together, what do I get? So u squared plus v squared is going to be e to the 2x cosine squared of 2x plus e to the 2x sine squared of 2x. And if I factor out e to the 2x, I get sine squared plus cosine squared, which is 1. So you will simply get e to the 2x. So u and v are related through x, and y has nothing to do with it. All that matters is x and how x is changing on this line. How y is changing is not important. And for example, now let's say if my x is 0, what does it mean? If I plug in x of 0 here, okay, and y of 0, so x is 0 and on this line, okay, this point is x of 0, y of 0, which if you plug in, it is going to give you u of 1, v of 0. So the point 0, 0 will come to here. Let me zoom in. So this is the picture of origin. Then if I have point 1 and 2, then the result of that is going to be, as you can see, it is going to be on a circle with radius of e to the 1, okay? But the angle of that comes from v over u, which is the same angle as y. So it is going to be 2 radians, and then so on and so forth. So what shape would you get? Let me show you. So in order to do it, I'm going to write a simple MATLAB code for you. And we're going to visualize this. So here, I consider a bunch of points in the xy plane where x is equal to, let's say, 0 to 2 with increment of 0.1, and y equals 2 times x. Now my function u is equal to exponential of x times cosine of y, and my function v is going to be exponential of x times sine of y. Okay, and now I'm going to plot v versus u. Or what I can do is this, say figure, and then on subplots, so subplot, let's say under each other. So it is going to be 2 and 1 and 1. First plot for me x and y. And title, you make it z-plane. And x label is going to be x, y label is going to be y. And then I have subplot 2, 1, and 2, where I plot u versus v, and this I call it fz plane. And the x's are u and v. And maybe I use a different color. And I and we're going to see them. So clearly that's the shape that you will get. the angle changes and the radius is getting bigger and bigger because it depends on the exponential of x, correct? So this shape will be converted to such a thing. And if I want, I can add more lines and I can see what it is doing, okay? So let me do this a little bit more for you. So I can keep adding to that, right? So one time I do it 2x, the other time I do it 3x, and so on. So maybe just for the sake of just show 3 of them. I don't need to keep going forever, but here I add 3 lines instead. Right, and then one category I generate with y1, I generate another curve with y2, and then with y3. So here I generate plot of x and y1, and then I say hold on, and then I generate the plot of y2 and y3. Similarly here, I can do something similar. So you can see it better. Okay, so if I have lines like this, the shape in the UV plane, it is going to be quite this tortuous curves, right? They are quite beautiful. So if I have now a boundary between these shapes, right, I have like a vertical line, then in this space, I'm going to get something different, right? So maybe I have y equal x, then I have y equal 2x, correct? And then instead of this third line, I might consider some line that goes from 1 to the corresponding here, so x stays at 1, y goes from y goes from 1 to 2, right? So I want to show you a closed contour here instead of 3 separate lines, and see the shape of that closed contour. Okay, so let me change the code a little bit. Okay, so here I change my contour so that instead of 3 lines that all start from origin and going somewhere, now I have a closed contour, like a triangle, and I want to see if I transform this triangle using the exponential function, what kind of shape I get in the UV plane. And this is the result. Quite interesting, right? It is kind of like a boomerang or a glider. So you can transform a triangle like this into a boomerang like that in the FZ plane. Okay, now what's the use of that? We'll get to it in a second. Why is it that this mapping can be any useful? So I'll tell you, but you clearly see that each one of those functions can generate nice shapes from Z plane to the FZ plane. You're gonna get some nice shapes, okay? So this is about mapping with complete. Each one of them has its own unique shapes. Now that we know about functions, there are functions and each one of them does the job of a mapping. First, I need to talk about what we call analytic functions and derivatives, and then I come back to the important question I ask, what's the use of that mapping? Okay, We learned that they can do a mapping. Okay, now what? Where do we use it in engineering? But before that, I need to tell you one more thing about complex numbers, that is analytic functions and derivatives, and then we come back and talk about that. So the definition of derivative is very similar. So if I have the function f of z, and I want to find the derivative of function f at point z naught, the definition is just a limit. So f prime of z at point z naught is equal to the limit of f of z minus f of z naught divided by z minus z naught as z goes to z naught. Okay, that's the definition of derivative, just like real numbers, no difference. The difference is the way that you go from z to z naught. That's the difference. What do I mean by that? Well, here you have some function, and this is point z naught. And this is z. How can z approach z naught? Well, there is no unique way. That's the major difference. That I can go from z to z naught in any way that I can imagine. So I can go on a straight line, I can go on an arc, I can go first backwards, then come, and so on and so forth. Okay, and this z is arbitrary, so my z could be here, and I can approach. My z could be here, and I can approach. So from all directions in any path, I can go from the vicinity of z naught to z naught. So that's this approaching thing that matters. Okay, and you can show that if the function has a derivative, and if the function is what we call, it is analytic, it has derivative, then the direction of this approach does not matter. Okay, in any direction that you approach the point of derivative, as long as there is derivative, the direction does not matter. All of these different ways of calculating this limit will end to the same thing. And I also want to tell you that, now what conditions for that is needed, I'll talk about it. But we can see that the derivative rules we have for complex numbers are going to be basically identical to what we had for real numbers. So, for example, if my function f of z is sine of z, which we defined in the previous page, then I can show you that f prime of z using this limit is going to be cosine of z. Now, am I going to go through the proof of that? No. But you can easily apply the limits and show that those rules we had for taking derivatives in calculus apply here, except for, let's say, for x, you replace it with z. So the derivative of sine is cosine, derivative of cosine is negative sine, derivative of z to the n is n times z to the n minus 1, natural log is 1 over z, right? So all of those rules we had in calculus will be applied for regular functions, okay? Nothing major. And so on and so forth. Now, let's go back to this derivative thing. We just learned that you can always write the result of applying your function to the variables x and y, or to the complex number z, is going to be another complex number which has two parts, u and v. Both of them are functions of x and y. Now, here there is this condition called Cauchy-Riemann Equations, and these conditions will provide you with sufficient necessary condition for the function f to have derivatives. Okay, it tells you whether your function has derivatives and is differentiable or not. It provides two conditions for you. It says the partial derivative of the u function with respect to x is going to be the partial derivative of the v function with respect to y, and partial of u with respect to y is negative of partial of v with respect to x. You can show that if the function is has derivatives and is analytic function, then these two conditions should be true, these two guys here. And what is analytic? Analytic means a function that has derivative. Okay, we say function f is derivative over a range if it has derivative at any point in it. Okay, and I can show you easily by just I'm not going to prove it, okay, this Cauchy-Riemann, but you can look it up for yourself. But I'm going to demonstrate that, for example, for one of these functions I just mentioned, maybe natural log of z or something like that, these two important equations, okay, these two conditions are valid, okay? So I'm going to show you that. And then they give you a way to calculate the derivative based on these partials. So now you can say the partial of ux and vx can be used to form the derivative of f, or the partials of uy and vy could, from these equations, could be used to calculate the derivative of z. Okay, so I'm gonna show you these two equations, one the conditions for it and the other one calculating derivative using these methods on maybe this function natural log of z, and then at the end I'll show you that you can also write it as 1 over z. Okay, so let's do a little bit of practice here. So what can we do? So if you remember, the natural log of z is natural log of r plus I theta, or you can also write it as this guy that I wrote for you, correct? 1/2 natural log of square root x squared plus y squared plus I tangent inverse. So let's do that. So f of z, which is natural log of z, is equal to 1/2, correct? Is 1/2 natural log of x squared plus y squared plus I times, and then we have what? Tangent inverse of y over x. And as we said, we call this function u of x and y. We call this one v of x and y. Now the Cauchy-Riemann equation says if this function has derivative, and it does for any z positive, with magnitude positive it has, then I have these equations that u of x equals v of y. So first, what is partial derivative of u with respect to x? So it is natural log of u, right? It's natural log of some function of x in general. So there's going to be the derivative of that over itself. So this 1/2 can stay out. And this is going to be the derivative of this guy with respect to x, which is 2x divided by itself, correct? So if you simplify it, it is simply going to be x over x squared plus y squared. By the way, now that I'm working on u, I would like to calculate the partial of u with respect to y. So there's going to be 1/2 and then 2y over the same thing. So there's going to be y over that. So this part is a good practice for your calculus, partial derivatives. So these are partials of u. Now let's do partials of v. So v of x is partial derivative of By the way, that's the meaning of partial, okay? So if you say u of x, what does u of x mean? Let me add it for you here so that you don't get confused. So here, u of x means partial derivative of u with respect to x. And for example, v of y means partial derivative of v with respect to y, and so on. Okay, so these ux, vy, these are first partial derivatives. So now going back, what's the first partial derivative of this v function with respect to x? Tangent inverse, as you know, is u prime over 1 plus u squared. So it's the derivative of this guy with respect to x, which is negative y over x squared divided by 1 plus y over x, the whole thing squared. If you simplify, you will get negative y over x squared plus y squared. And then partial of v with respect to y is going to be derivative of this with respect to y, which is 1 over x, over 1 plus, again, y over x squared, which is going to be x over x squared plus y squared. And now look, partial derivative of u with respect to x is the same as partial derivative of v with respect to y. These guys are the same. And partial derivative of u with respect to y is negative of partial derivative of v with respect to x. Since these conditions are there, then I can say that my function f of z is an analytic function and it has a derivative. Okay? It has derivative anywhere that these two conditions are valid. And these conditions are always valid except for where x and y are both 0, which is at origin. So this function is analytic everywhere except for at the origin. Now, what's the derivative of this function? Based on what we had up there, the derivative of this function at arbitrary point is ux plus ivx, or vy negative I uy. Okay, now here let's just replace ux and vx, so it's x over x squared plus y squared plus I times negative y over x squared plus y squared. Now, is this the same as 1 over z? Well, let's find out. 1 over z is what? Is 1 over x plus iy. And here I have divided two complex numbers, so I multiplied by the conjugate of the denominator. And as you know, it is going to be x minus iy divided by x squared plus y squared. And guess what? This is the exact same thing as above, correct? Just separate them. Right? So you clearly can see that the derivative of natural log is the same as what? 1 over z. Okay? So here I told you the conditions necessary for a function to have derivatives called Cauchy-Riemann equations, these two equations. And if these are valid, then the derivative of the function can be found by either of these, okay? Either this one or this one of them, doesn't matter. And not only that, then if I plug in, if I take double derivative of ux and uy, or vx and vy, I can show that u and v, these two functions, they both fit into this equation here, where double derivative of u with respect to x plus double derivative of u with respect to y is going to be 0. And this double derivative, sum of the two double derivatives of any function with respect to its variable, is called the Laplacian operator, or nabla, or del squared. Okay, and that is not hard as well to show. So if I say, what is uxx plus uyy, this means the partial derivative with respect to x of ux, and this is partial derivative with respect to y of uy. Now ux, as you know it, is equal to vy, so this is this. And uy is negative vx. Correct? So this is going to be partial derivative of x of v, which is with respect to y already. Correct? So this is like second derivative of v with respect to x, and then y and then x. This is negative of second derivative of v with respect to y and x. As you know, these two guys are equal, so the result is what? 0. Okay, so the sum of these two second derivatives of u or v with respect to x and y, this summation is equal to 0. And so this is what we call del squared of function u, or Laplacian operator. Okay, so again, the name of this guy is called the Laplacian operator, del squared, which means the sum of the two partial derivatives. Okay, so if you ever heard that, and we're going to use this a lot in engineering in higher levels. And what is this really doing? What's the meaning of this Laplacian operator? Well, if I want to put it in plain English and explain it in a simple manner, this Laplacian operator measures the smoothness of the function. Okay, so remember, for example, derivative does what? It detects where the function is changing rapidly or slowly or something, right? It's like a filter. The second derivative gives you the curvature. Now what this one does, it measures the smoothness. If a function u as a function of x and y is a smooth function, so it's changing smoothly with respect to x and y, then the Laplacian operator of that is 0. And if it's not 0, small, and the bigger this number is for any function at any point, means the function is changing rapidly with respect to x and y, and it's not smooth. Okay, so it's called Laplacian operator, and you can show that u and v, the components of function f, they both fit into this Laplacian equation, where the Laplacian is equal to 0. And therefore, it means that also, again, I don't want to get into too much detail of that, it means u and v should be harmonic functions. We call them harmonic functions. Okay, so let's not get into too much depth of that. But for the moment being, these are the conditions for derivative and how to take derivatives, okay? Now, let's go back and talk about why is it that these mappings that we learned here, we learned each function is doing its job, correct? It is taking x and y plane and convert it into something in the uv plane. What's the use of this, what we call mapping? Well, one specific type of mapping comes from functions which are analytic. And what these functions can do, these f of z's can do, is they can create what we call a conformal mapping. What is conformal mapping? Conformal mapping means it preserves the angles. What does that mean? It means if I look here, let's say this is the z-plane, and in this z-plane I have this grid of x and y. And if you look here, I have a horizontal and a vertical line intersecting each other at a 90-degree angle. Correct? If I project these two black lines onto the FZ plane using this specific type of function we call a conformal mapping function, then you will get probably this curve and this one. But again, where they hit each other and intersect, that angle is 90 degrees. Okay, so it might change the shape, and it does change the shape, but it preserves the angles where these different contours intersect. Okay, and this is very important property in many applications, that when you do this mapping, the angles are preserved. Not necessarily every map, every function provides a conformal mapping. Okay, we need some condition for a function to have a conformal mapping, but this conformal mapping, as I said, this type of map especially, is very important. Now, why is that? Let me tell you. So what conditions does F need to do this conformal mapping? The condition is over this range that it is applied, at each point it has derivatives. Okay, it has the z derivative as we described in this previous page, and also the derivative of this function at no point along any of this path is equal to 0. So as long as f of z is differentiable over the domain it is applied. And the derivative, first derivative of z with respect to z at any point is not equal to 0, then we can say f of z could provide a conformal mapping. Now, what's the importance of this? What's the use of this in engineering? Okay. As I said, one of the places that this conformal mapping can be used is the fluid flow around objects, okay, the potential fields, okay, and how the fluid, any water, whatever, is flowing around an obstacle, an object that is on its way. So let's say I want to see what is the flow around an airfoil. So I'm studying an aerodynamic problem, and these are the basically fluid flow lines. These are the streamlines around the airfoil, and these guys that are perpendicular to these streamlines, we call them the potential lines. So phi here is the potential field, and you can show that if the flow here is not rotational, Okay, so there is no spinning in the flow, and this fluid does not have viscosity, or the viscosity is negligible. Then the potential field, the equation for this potential field, these lines, these contours, follows this important equation we just mentioned, the Laplacian equation. Okay, and when this happens, it means that I should be able to find the this function that comes from this phi and then this size, which are the streamlines. If I form a complex function from phi's and size, where again size are streamline functions of x and y, and phi is the potential field of x and y, then that function is differentiable. And now what? Now somebody with the name Joukovski, he came and showed that he can offer you a conformal mapping which takes you from a circle to what? To an airfoil. So he said that if you have a circle in the xy plane, if I applied this function, z plus b squared over z, the whole thing divided by 2. If I applied this complex function to this to this circular contour in the xy plane, then in the uv plane, the projection of that is going to be an airfoil. So now what? Now, instead of me solving my fluid problem in this UV plane around the airfoil, I apply the inverse of my function and basically take everything from the UV plane back to the XY plane, where everything is to be solved around the circle. And in partial differential equations, for the equations of the fluid around the circle, there is analytic solution, because again, I don't want to make it super intensive math, but when you're solving partial differential equations, I'm going to make a separate video on that. When you're trying to solve partial differential equations, here the equations of flow for the fluid, these partial differential equations you cannot always solve with every boundary that you can imagine. For some very simple boundaries like the circle, those fluid equations, those partial differential equations, they have analytic solutions, but not for an airfoil. Okay, airfoil is not such a nice regular boundary over which you can solve the equations of fluid flow, okay, or find the potential fields or anything like that. So here in this space, I have analytic solution. Okay, this space is good. I'm solving the flow over a nice boundary. Here I'm not. But if I call this function w or f of z, whatever you want to call it, with f, I can go from this space to this space with f of z. Now, if I can find inverse of f, which in this case is quite easy actually, with applying the inverse of f, I can go from this hard boundary to this easy boundary. So instead of me solving the problem here, I solve the problem here, and then I apply my complex function, is what we call Joukovski transformation, this guy. I apply it, and that means I could get my analytic solution around the airfoil. And that is very important, right? As you know, analytic solutions are extremely important for predictions and so many things. Yes, we can solve partial differential equations around any boundary using numerical methods. As I said in that lectures I'm going to publish on PDE, I'll show you. You can use finite difference, finite volume, and so on, and solve this problem, finite element. But if there are just going to be a bunch of numbers. At each grid point, they are going to give you some number, and in between them you have to do interpolation. There is no analytic function. There is pure numerical solution. So since I have the analytical solution here, now I can use this transformation, and what? I can find, see, no. Okay, this guy is not going to be cooperative. Okay. So for cylinder, analytical solution exists. Now, thanks to this transformation, I can apply this transformation to that analytical solution around cylinder and find the analytical solution for what? For the airfoil. Once I know the phi's and the size and the equation of them, it is going to be really amazing for predicting how the fluid, like air, would behave around the airfoil. Again, this here is, it needs your flow to be inviscid, which means no viscosity, and non-rotational. If my fluid is not rotational and it's not showing any viscosity, then under these two conditions I can find an analytic solution around the sphere. So it's not like I can find the analytic solution for any condition under a sphere. No, I still need some preconditions, some assumptions to find this. But if those exist, then I can find this and then transform it to the actual around the airfoil. Okay, so this is one application, and there are so many other applications in electromagnetism and so on, where you are trying to find the potential fields of an electric or magnetic field around a wire or something. You can use this conformal mapping. And this conformality is very important, because if it cannot preserve the angle, then these angles you have here are not going to be preserved in this one, and that means the direction of these streamlines are going to be different from here, and that is not a good thing. Okay, whatever here is, you want to have in the other space as well. The directions do matter. So if you preserve the angle, you can preserve the directions. And so these conformal mappings, and in general these mappings like this, are very important, right? For as I said, solving partial differential equations around irregular boundaries, around hard boundaries. We try to see if we can find a simple boundary over which we can easily analytically solve, and then using that mapping we can bring and convert that simple boundary into that hard boundary. Okay, so as I said, this is a little bit above the level of most undergraduate courses on complex numbers, but I want you to know about it. Okay, now I have a couple of more things I need to talk about, and the next topic is integral of complex functions over contours. So what is that one? So here the goal is, if I give you this complex function f of z and ask you to integrate this function over this path or contour C, can you do it? What's the definition of it? How would you do it? And some relevant theorems and lemma for this integration. So first of all, the integration of complex numbers, just like integration on real numbers over any path or contour, has this linearity property. If you change the upper and lower limits, or basically what we call change the sense or the direction of integration, then the result will be negated or negative of the what it used to be. And you can also split an integral into smaller parts, right? So you can break down the contour C into C1 and C2, and instead of integrating f of z over C entirely, you can integrate it over C1 and C2 and add them together as long as the direction of moving along C1 and C2 is the same. Okay, so you have this splitting property, the change in the sense, and linearity property of this integration, and they would help a lot when we do integrations. Now, how would we do it? One way to do it is if we can find the antiderivative of f of z based on those derivative formulas that I told you, right? That basically, well, let's see if I can find it. That many of the derivatives we have in complex numbers are similar to the calculus, then definitely the antiderivatives, right, are similar to real numbers as well. So when we integrate 1 over z dz, then the result is natural log of z. When we integrate cosine of z dz, the result is sine of z, and so on. So one way is using this basic theorem of integrations, where it says the definite integral of f of z dz is the antiderivative function cap f calculated at z1 subtracted by that function calculated at z0. And here this cap f, if you take derivative of this cap f with respect to z, the result is the small f. Okay, so cap f is the antiderivative of small f. Okay, so one way is, if you know that, you can find it that way. The other way is to do it parametrically. So try to describe this path or curve or contour, whatever you call it, in terms of some parameters. So the real part of it as a function of a parameter, as well as the imaginary part of it, and then do it parametrically. So here the z dots of t dt, this guy here is dz. Okay, if z is a function of t, then dz is going to be z dot dt, and then if the value of that parameter at the beginning and the end point is a and b, then you integrate this function from a to b. So the other way to do it is using parameters. And here I try to give you a couple of examples for these guys, and then we try to go to the next topic, which is the Cauchy's integral theorem and so on. But right now, to provide you first with a few examples, one for each one of these methods, and then, as I said, we go to the next topic. Let's, for example, say that my function f of z is whatever you want to call it, let's say z squared, and I want to integrate that over, let's say, a contour like this, which is, let's say, just a simple line. And it goes from point 0 and 0 to point 1 and 1. So this is my contour C in this case, a simple line, and my function f of z is z squared. Right? So how do I integrate f of z over this contour C? Okay, so let's do that. So if I go with this fundamental theorem for calculating definite integrals, it is going to be from z here, this is z naught, this point, and this point is z1. Clearly z1 is 1 plus 1i, and z naught is simply 0, 0 plus 0i. Correct? So these are the upper and lower limits. And so it is going to be from, as I said, 0 plus 0 I to 1 plus 1 times I. The function f of z dz is going to be z squared. And we know the integral of z squared based on what we know from calculus of real numbers is z cubed over 3. That's the same thing for complex numbers. So this is going to be z cubed over 3 evaluated at those two upper and lower limits and then subtracted. And clearly it is going to be just this number cubed over 3. So it is going to be 1 plus 1i cubed over 3, which if you do it, you know that 1 plus I cubed is going to be 1 plus 3i plus 3i squared plus I cubed over 3. And here I can simplify. This is going to be negative 3. This is going to be negative I. And so the result, if you simplify 1 and negative 3, that's negative 2. So this is going to be negative 2/3 for the real part. And this is 2i over 3. So this is the imaginary part. So the result is negative 2 over 3 plus 2 over 3i. Okay, that's if we do using the fundamental theorem of definite integrals. The other way to do it is, as I said, we can do it parametrically. So if I consider an arbitrary point along this path and call it point z. So here, let's consider some arbitrary point here. Call it point z of t, which is x of t plus I times y of t. Okay, where this is your y and this is your x. And clearly you know the equation of this line, since it goes from 0, 0 to 1, 1, is y equals x, correct? So on this line, clearly y is equal to x. So if you want, you can plug it in that. And so it is going to be like x of t plus I times x of t. And t, clearly, since x goes between 0 and 1, and y goes between 0 and 1, so clearly t here can go between... well, first let me write it that way. Now, before I talk about this, now the question is, what would you choose x of t to be? Okay? Now here is your choice. What do you want your function x of t to be? And I can go with the simple choice of, since I want t to constantly change between two limits, and for that x changes, so here I choose my x of t to be t, and therefore this is also going to be t. So my z is going to be t plus I times t, where t can change between 0 to 1. Okay? And so now if I want to do this integration using the parametric method, then this integral of t from initial value to t to the final value of f of z of t times dz. Correct? Or you can say z prime of t dt if you want to go with this formula. Doesn't matter. So let me do it with that formula. So z dot of t dt. Okay, where z clearly itself is equal to t plus it. From here, if I calculate the derivative, clearly z dot of t is going to be 1 plus 1 times I, correct? And z dot squared is going to be t plus it squared, so it is going to be from 0 to 1 of t plus I times t, the whole thing squared, times the derivative, which is 1 plus 1i, and then dt. Okay, and if I continue that here, I'm going to get integral from 0 to 1 of, here I square it, this is like t times 1 plus I, correct? So if you factor out t out of this guy, you can write it as t squared times 1 plus 1i squared. And here you have 1 plus 1i, so this is going to be 1 plus yi cubed. dt. And t squared dt is going to be t cubed over 3. And 1 plus 1i cubed, it is going to be this guy, correct? You clearly can see it. The result of that is negative 2 plus 2i. The whole thing is evaluated at 1 and 0, which clearly this is going to be 1 over 3 multiplied by that. You're still going to get negative 2 over 3 plus 2 over 3 times I, which is the same as last time. So it does not matter which method you choose, whether the parametric method or directly using the fundamental theorem, the result of calculating a complex integral over a path should be the same. Okay, so this is about the meaning of calculation of that and the properties that this integration over path does. Now, some important things about this integration. One is the Cauchy's integral theorem. It says if function f of z you are trying to integrate is an analytic function, analytic, you know, it means it has derivative at any point on that domain, and it's also simply connected. It is analytic in a simply connected domain D. Now, what does simply connect mean? So a simple contour, if somebody says what is a simple contour, it means at no point the contour is intersecting or touching itself. Whenever the contour is touching or intersecting itself, it's not a simple contour anymore. If it keeps the distance from the rest of the points, then it is simple. Now, simply connected means what? Means if you basically shade the area that is enclosed by this simple contour, you will only get basically one inside and one outside, okay? If like this, when you connect these parts of this contour, so this contour has two portions, if you do that, now you have three regions, this region, and this region. While here, you only have inside and outside. Okay, so if you divide the space into two regions, enclosed and not enclosed, then it's simply connected domain. If you get more than two regions, so like inside, outside, and on the domain, within the domain, then it's called double connected, or you might get triple connected, depending on how many of these inner contours you have for the overall contour. So what I'm talking about is this. Your function f is analytic in a simple domain like this, so your contour should look like that. and not like this, then it says the integral of f of z is independent of pad in D. So it doesn't need to be necessarily on this boundary contour. If you go from any point on this path to any other point, it does not matter how you go, okay? The result is the same. So what does that mean? It means if I go from this point to this point, if I go by a straight line, if I go by any other type of curve like this, correct? Then if I call this one C1 and if I call that guy C2, then the integral of f of z dz over C1 is the same as the integral of that over C2, and that's what you can see here. So here, this domain f of z is defined over f of z is analytic on that, and that domain is simply connected. So it doesn't matter how I go from z1 to z2, go from this path c1 or from path c2, the integral result is the same. Okay, that's the important Cauchy's integral theorem. It doesn't matter how you go from beginning point to the end point, as long as your function is analytic on a simply connected domain. And that will also make the fact that if you start at z1 and go around and go back to z1, the integral on a loop, on a closed contour, is going to be 0. Wherever you see this symbol on an integral, okay, wherever you see this symbol on any integral means it is made over a closed contour. So here your contour should be closed. The beginning and the end points are the same. Okay, and the reason for it is the integral here over c, if I call this whole thing c, can be written as over c2 plus over c1, but in the opposite sense. Okay, so it is going to be like this. But remember that since in here I'm going opposite to the direction of c1, it is going to be like that. Right? We just know that when we change the sense of the integration, it is going to be negative of what it was. So now, right, now this integral here is going to be negative of c1 plus c2, but the thing is, the integral of c1 and c2 are the same, as we just saw, right? The integral over c1 and the integral over c2, they are the same. So when we say negative over c1 plus over c2, the result is going to be what? 0, of course, okay? So integral of analytic function in a simple domain on any closed contour is going to be 0. That's another way to put the Cauchy's integral theorem, okay? And this is important. So this is one of the important things I wanted to talk about. And now there is one more thing we have to talk about, and then we go back again to application in engineering. So another important formula by Cauchy is its integral formula, or sometimes we call it the residue formula, and it says that now this function that you have f of z and you're integrating it over some contour, inside the region enclosed by the contour there are some poles, there are some points at which the integrand of the integral goes to infinity. Like this case, I'm trying to integrate f of z over z minus z naught, okay, and the z naught, point z naught, is inside this contour c. Contour c is enclosing point z naught, which is a pole of that function. Okay, so this function, this integrand I'm trying to integrate, it has a what? It has a pole at point z0. Okay, so again here, your contour C encloses that point. Then, when I integrate my integrand over this closed contour, the result is not going to be 0 anymore. Because there is one point at which this function will be infinite inside that contour. And so, there is this point z0 at which this function is not analytic. It says if such thing happens, then this integral over this closed contour is going to be 2 pi I times the value of this function except for the pole. Forget about the pole, look at the rest of the integrand. So f of z is the rest of the integrand except for that pole point. If you evaluate that rest of the integrand at that pole, f of z0, multiplied by 2 pi I, that is going to be the result of the integral. And the value of the remaining of the integrand at that pole is the term we use in complex numbers, we call it the residue. So we say this integral of this function or over a contour that encloses some poles is 2 pi I times sum of the residue. So sometimes you have more than one pole. What if this contour that you are trying to do, so here what you have is you have this contour C and it encloses point z0. So when you integrate it, the result is 2 pi I f of z0. What if you have another point like z1 that also appears in the denominator here? So for example, you are doing something like this. F of z, correct, times z minus z0, and then times z minus z1. Then what? dz over c. Then you have to calculate the residues. For one of them, it is for z over z0. For z over z0, it is going to be this function. You have to evaluate this function at z equals z0, and for z equals z1, it is going to be this function that you calculate at z1 and then times 2 pi I. So the result is going to be like this: 2 pi I times f at z0 divided by z0 minus z1 plus f at z1 divided by z1 minus z0. And this is the residue at z0, this is the residue at z1. Add them together and multiply it by 2 pi I, okay? So it is 2 pi I times sum of the residues. Okay, this is the important integral formula for Cauchy, and it has a lot of applications. One of that you might say, okay, you said all of this, now show me where I use this integral of complex numbers, anywhere in engineering. And I tell you right off the bat, inverse Laplace transform is one of the places that you can use integral of complex numbers. Seriously? Yes. Because if you remember, as long as you probably remember, you always have done inverse Laplace transform using partial fraction expansion, right? And there is one of the videos in which I talked about this. But the direct method of calculating the inverse Laplace transform is integral of f of s, which is Laplace of f of t, e to the st ds, over a line which goes from sigma minus j omega, where omega goes to infinity, to sigma plus j omega, where again omega goes to infinity, and then the whole result divided by 1 plus 1 times 2 pi j. And here j is the same as I, the same as the complex base. What does that mean? It means, first of all, what is this? Well, as I said, it is a line with real part sigma. So this line, it is this line C1, for which the real part is all sigma. It's a vertical line. And then it is an infinite line. So the end point of it are literally going to what? To infinity. So this point is going to infinity. This point is going to infinity. Okay, so this is basically a complex number, right? If here you consider your s to be the complex number. And so it is like, this is similar to integral over contour C1 of f of z e to the z times t dz. Okay, so that's what I'm doing. Now, how can I use it? Let's look at it with one example. So here I'm trying to calculate the inverse of the function 1 over s plus a. Well, you all know from your Laplace transform tables that the inverse of this is, as you know, it is e to the negative at. Correct? I assume you all know that. But how can I get it from this integral? Well, let's take a look. So what I try to do is first calculate this integral, and then we'll multiply by 1 over 2 pi j. So what is integral of this function f of z, correct? E to the zt dt. So here instead of s, I'm replacing it with z. So this is s-plane or z-plane, doesn't matter. You can call it the same thing. And what is that? Well, here, the root of this f of z is happening at z equal negative a. So if I want to write it, it's going to be over c of e to the zt over z plus a dt. So this is what you need to calculate. And clearly, this guy here has a pole at z equal negative a, depending on where negative a is. So if we assume a is positive, then negative a, which is the pole, is a negative pole. So it will come here. Right? So let's say this point here is negative a. And now the question is this. When you select this C1, you have a parameter to choose, and that is the real value sigma. How would you choose sigma? Well, you are free to choose sigma as long as when you draw this line and then connect the two endpoints using an infinite semicircle, then in this contour formed by this semicircle, you should always enclose this pole. So in this case, the way I made sigma, I do not enclose inside this D-shaped contour the pole. So what I need to do is bring this guy to the left, correct? So what I need to do is choose a negative sigma like this. Okay. Oh. What is going on? So I choose a negative sigma smaller than negative a, and I do something like this. Now I can call this one C1, and here I choose my direction of C2 to continue like C1. And now I have this closed contour, which we call C. So C here means C1 union C2, okay? So C is the whole thing. Now, does C have a pole in it? Yes. So if I want to integrate the function over this C, correct? If I want to integrate this function, instead of over C1, I just want to integrate it over the entire C. Then the result of this should be what? Should be 2 pi I, based on what I know here, times the value of this function, correct, evaluated at the pole, and pole here is z equal negative a, correct? That's the same as z naught for here. So it is going to be the value of this function evaluated at negative a. So for z plug in negative a, it is going to be e to the negative a times t. So this is the integral of the complex function over the entire closed path, right? Now, if I want, I can say that the integral of the function over this entire path is equal to the integral of it and by the way, this is d z, not dt, over C1 plus the same thing over C2, correct? I can break it in two parts and add them together, right? So now, if I know how much this one is, I can take it to the left-hand side, subtract it from this, and that will give me what I wanted. Now, what's this integral of this function over C2, this arc, which has an infinite radius? So the radius of this guy is infinite. To calculate that, there is this lemma called the Jordan's lemma, and it says, as long as your function f of z is continuous over an arc with a radius of infinite, the integral of f of z dz over c is going to go to 0 when what? When r is clearly infinite. Okay, so it's not always 0, but if r is going to infinity, then the integral over this arc, as long as f of z is continuous over only the points on this arc, not inside anywhere, just any point along this arc is f of z continuous over that, then the limit of this integral as r goes to infinity is 0. And that's the same thing here. This function I'm trying to integrate, this guy, is continuous over any point along this arc. There is no problem with that. So the second integral is equal to 0. And so the integral of C1, which is this portion I was looking for, is clearly equal to 2 pi I e to the negative at. Therefore, f of t is going to be what? It is going to be 1 over is going to be 1 over 2 pi I, and this portion of the integral, which is this integral over C1, we just calculated here. As you can see, it is 2 pi I e to the negative at. And guess what? The 2 pi i's would cancel out. And you will get e to the negative at, which is the inverse Laplace of this guy. Okay, so we can easily perform an inverse Laplace for this function 1 over s plus a. And if you know this and you know how to perform this fast, then this integral here can actually faster calculate some of your inverse compared to partial fraction expansion. It's just you need to know how to integrate and how to use this Cauchy's residue or integral residue formula. Okay, as long as you know this, calculating inverse Laplace transform is not that bad. Okay, so I told you some important stuff about complex numbers, their functions, and that the functions can create maps. A special type of map that preserve angles we call conformal mapping, and those are used to solve partial differential equations for us PDEs over basically difficult boundaries under special cases. We talked about taking derivatives of complex functions. Where is it that they are differentiable and the functions are analytic? The Cauchy-Riemann equation, and then the Cauchy's equation for integral, and the integral of complex functions over contours. Okay, so I'll stop the lecture here and I will see you next time. Thanks.